and I will carry on admitting you while Aviva will tell us about her background and indeed whatever you want to talk about before we begin. So Aviva, over to you.
Okay, I am a professor at the Courtauld, which combines a gallery and an institute for the study of art history, conservation and curating. Specialist College of the University of London, and I've been there for exactly 30 years now. Before that, I was at the National Gallery in the Scientific Department, National Gallery London. And prior to that, I did a degree in neurobiology at the University of Sussex. But because I wanted to go to art college, but it wasn't a really financially feasible thing, I decided to do something that combines art and science, and so that's what led me to conservation. So I trained as a conservator of paintings at the Courtauld, then I did a PhD at the Courtauld after that, after working in Australia, which is where I was brought up. I worked in the Art Gallery of New South Wales in Sydney, but I'm from Melbourne in Australia, but I was born in New Zealand, so very complicated. But I'm back in London now, and I have been for the last 40 something years. But yeah, that's my background. So yes, I supervise people, postgraduate students in easel painting conservation. They turn out to be professionals in easel painting conservation quite specifically, and they work worldwide in museums and in the private sector. That's my main focus, but my specialism is in technical study of paintings, which is absolutely critical to the diagnostics for conservation. So we need to know how paintings are made and how they've changed before we can decide how best to conserve and display them. So I'm going to talk about that side of things for you today.
Okay, thank you very much. I'm just giving us one moment longer. I think we've reached a stable number of 6 people. Having said that, 6 people have just come into the waiting room and I will be admitted. Okay, so we're now up to 46 people, another 3 people. Okay, okay. Okay, so we're now up to 47 people. I'm sure more will join us in the next few minutes. But perhaps, Aviva, you could start to give us your talk on material matters.
Okay, well, thank you for inviting me. I'm really happy to talk about the subject. So what I'm going to talk about today is the work that I do at the Courtauld, or that has been done at the Courtauld, because Peter said that you're interested in history. So I'm going to weave in some historical images of the kind of work that was done and the kind of history of the Courtauld's role in technical study of paintings. I'll talk about the developments of methods for material analysis and imaging of paintings. And I'll show you some examples of what lies beneath the surface of paintings and what this tells us about artists' working methods, first and foremost, and very important for conservation, how works of art have changed with time, or even changed quite soon after they were made, and how we consider that in how we view works of art and perhaps how we preserve them. So at the very end, I'll talk a bit about conservation, just very lightly, but mostly about the technical study of paintings. Not sure I'm able to move the slides on. Don't seem to be able to move the slides onto the next slide. Let me see if I can do that. Yeah, there we are. Okay, so first of all, a bit of history about the department that I work in. The department was set up in 1932 when the institute was set up, and it was initially set up not for conservation at all, but for technical study of paintings, which helps to inform elements, some questions in the history of art, how something might have been made, who might have painted it, and the materials that were used for it. So that was the focus of the initial, the remit of the department from 1932. And I'm going to show you a few slides of the department, both contemporary and historically. So you can see some quite old-fashioned 70s looking images here. And in the 70s was when the conservation element was set up. So right from the 30s to the 70s, it was literally for technical study of paintings, not for conservation of the paintings, but a postgraduate course was set up in the 70s which now is one of the leading courses in the world. So here are some really old historical photos. A picture of Samuel Courtauld, who's one of the founding members of the Institute, whose painting collection, and in particular, collection of Impressionist paintings is in the Courtauld Gallery, which is at Somerset House. And I hope some people have visited it, because it's a really marvelous collection, not just by Samuel Courtauld, but also other donors to the collection who've added their amazing works of art, both paintings and also some sculptures and other decorative arts, all displayed in a lovely refurbished gallery in Somerset House, newly opened. So what you can see is some images that I found from the archive of early founding members. P.D. Ritchie, who was the first head of the department, and you can see him on the lower left. He's got a kind of visible light spectrometer, which was used for analysis of paint. And he's also looking in a very early X-ray. The Courtauld was one of the very earliest institutions to X-ray paintings in the UK. And a picture of the use of binocular microscopes. Now we've got more sophisticated microscopes, but that was the starting point, an old fume hood, and the accommodation at Portman Close, behind Portman Square, which is where I was a student in the early 1980s, student in conservation. Another picture of Professor Stephen Rhys-Jones, who took over after the war as a scientist. He was there when I started. It shows how old I am. And you can see him looking with P.D. Ritchie at a famous forgery by Haan van Meegeren, a forgery of Vermeer, which was actually given to the Courtauld, to the department, by a soldier after the war. Van Meegeren was a very famous forger who managed to sell paintings that were supposedly by Vermeer to the Nazis. Since then, technical study has revealed them to be wrong. And this is quite a good one, the one we have. This is a slide which shows my own teachers in conservation, who were, and the reason I show them was that they are a great example of how my field is really collaborative. It involves conservators, who are very practical people, art historians who know about the history of art and when things were made and where and by whom, and then other people who have different skill sets, like engineers, chemists, physicists, and other experts, and these people have to work together, and that's still the case today. For the best work that's done is collaborative, and people have to understand each other, and most of all to appreciate the works of art that we are focusing on. This is an image of the Department of Conservation today. We have something like 5 or 6 students per year, so a very small cohort for a 3-year postgraduate course, and we do practical work on paintings from the Courtauld Gallery, from regional museums, and from private collections. So we choose very carefully, not destroyed paintings, but really good paintings for students to work on. And you can see some students here working on, and one was working on the Bruegel on the left from the Courtauld Gallery, another is working on paintings from Tate, and then you can see students visiting the department in Florence. So we have an international perspective on what's done. And on the right, you can see somebody doing experimental work. We also have a very high research profile. So there are many questions in conservation and material research on paintings. Lots of unknowns, and students at this level can do very good original research work, and that's something that I'm very interested in supervising. So the thing that I'm going to focus on talking about is materials and techniques used by artists and how they change with time, just to show some examples. You can see some images here of artists who work in different ways, and the kinds of palettes of pigments which change over time, which gives a kind of benchmark for when they might have been made. Sadly, there aren't so many benchmarks. Really, in the 19th century is when most new pigments were developed. So you've got from the Middle Ages to pretty much to the 19th century or the 18th century, when there was a pretty consistent use of pigments for painting. So you can't really date paintings based on pigments, but you can get an idea of when something was painted by the techniques of paintings that are used, the kind of preparation layers on canvas, wood, or on metal supports if they're portable, and how those materials are mixed and applied. And you can see there's a picture of Jackson Pollock. So people, 20th century artists, who threw paint onto the canvas, rather different technique than the very refined technique that was used perhaps by Netherlandish artists, or the outdoor painting done by Impressionists in the late 19th century. So paint is fundamentally a mixture of a binding medium and pigment. Coloured pigments can come from different sources, so they can be man-made or they can come from mineral sources. Traditionally, they were ground up in small organizations or artist studios. And then later on, and you can see on the bottom right here, they were made and manufactured really from the 18th century onwards by big colour merchants who then sold them in bladders initially, pig's bladders. They were contained there to stop them drying, mixed with the oil binding medium. And later on from 1841 in collapsible tubes, which allowed people to go outside and paint, stop the paint from drying solid inside the bladder. And you can here see the materials are ground up on a slab. And then here I've just shown you 3 different sorts of oil. There's linseed, walnut and poppy oil, which were typically used, drying oils that typically mixed with pigments for painting. Of course, artists also used egg tempera, so either a mixture of whole egg, the yolk and the white, or just the yolk for a sort of thick tempera, oily tempera paint. And they also use watercolor and gum type media, gouache. So there's a range of binding media that are used for easel paintings. I'm going to talk about oil painting and tempera painting. So how do we find out about artists' techniques? Well, there are quite a few nice images of people painting in their studios historically, which gives us an indication of how things were done in previous times. I've got here details from a 17th century painting, Dutch 17th century painting, where you can see that the canvas was stretched on a kind of frame by looping strings around the edge of the canvas. And you can see the range of pigments that were used for painting at the time, which we can analyze and we can identify. We also have information from paintings that like this is by Martin van Heemskerk, again from the 17th century, 16th century, which show that at that time a grey background was used, and then the paint was put on top after having quite a detailed underdrawing, which you can see here. So sometimes the paintings themselves present information about historical painting techniques, but very often we have to do different sorts of technical analysis to find out how it's done. So in the 19th, again, historical reference here to the methods that were used really at the beginning of the 20th century. It's developed over the 20th century. There are a number of techniques that have been used to identify materials in paintings and look at paint layers. And I've shown you here, I found this image of Joyce Plesters and her publication in 1956, where she developed a method for looking at paint layers from very small paint samples. And that's something we use till today for looking at paint layers. So she was fantastic in her seminal work. You can see her working under the very old-fashioned looking microscope with Raymond White from the National Gallery, who was the organic chemist. So she was inorganic chemist and he was the organic chemist in that partnership at the National Gallery. In fact, both those members of staff were there when I worked at the National Gallery once again. So I learned from the masters. So what you here have as a diagram of a paint layer construction. So you have the canvas or perhaps wooden support or maybe metal support or slate sometimes. It's not necessarily canvas. And then there's some kind of preparation layer, which we call a ground. There could be more than one ground layer. Then could be drawing that draws out the composition. And on top of that, a series of paint layers, different sorts. And then finally, perhaps a varnish layer, not always a varnish layer. In the 19th and 20th centuries, artists preferred to leave their pictures unvarnished, but very often earlier pictures have been varnished. Indeed, 20th century paintings have also been varnished against the artist's wishes, but they're usually dead for other reasons. So samples are taken and viewed under the microscope, and I've shown you some of the samples here. They're embedded in resin, and you grind them so that you can see at right angles the paint layer structure. They're very tiny samples, and in this box you can see there's a picture of me when I was young, looking under the microscope at Courtauld at some of these samples. And you can see samples here, right in the middle here is, I don't know if you can see my cursor, you probably can't. You can see that there's a tiny sample embedded in there, and these in the box, you can see that samples have been prepared for elemental analysis using electron microscopy and EDX spectroscopy. And they have to be carbon coated. Not always, but they have been carbon coated in this case. So what do the cross sections show you? Well, this is just a really good example taken from Joyce Plesters, so very early on. So the paint cross section, a tiny sample the size of a breadcrumb or smaller, so long as you can see it and it contains all the layers. It can be very tiny microscopic samples, so we don't sacrifice a lot of the painting. It's not ethical to do that. And indeed, we only take samples from the edge of damages or the edge of the painting, never from the middle of an intact paint layer. There are sort of ethical principles involved. it's very useful to look at layer structure. And so the sample was taken here from the red sash around the shawl of Ariadne. This is from a painting by Titian in the National Gallery, Bacchus and Ariadne. It's a very famous painting. So the sample was taken here from there. And in the cross section, you can see the top red paint layer, which is vermilion. So it's mercury sulfide, it's vermilion. And you can see it's been painted over her flesh paint, which contains these layers here. So a pink layer and a top paint layer that contains a lot of pink and a red lake pigment and some ultramarine blue pigment mixed with lead white. And then that flesh paint's been painted over the water in the background, or the sky in the background, which is blue, and contains these big chunky particles of ultramarine and lead white. And then here is the priming on the canvas, or the ground that's on the canvas, the preparation layer, which is usually a calcium sulfate in this case. So you can learn an awful lot from a tiny little cross section about the paint layer structure. And I haven't got the scale bar on here, but we're looking really about 20 microns thick, so quite thin paint layers. And so the resolution of analytical resolution is quite challenged by these thin paint layers in easel paintings. Why is it important to know what's in a paint film? And I thought I'd just show you a few images to really give you a sense of the difference in binding media. So you have the inorganic pigments, or you might have organic colored materials mixed with an organic binder, which could be oil or egg. And I'm going to contrast details taken from different paintings where oil is the binder and egg is the binder. And I hope you can see the difference in the painting technique. The thing about egg tempera is it dries really quickly. So you apply the paint and it's dry almost instantly, which means you can't blend the paint as you can with oil paint. So you see in this foot, this Renaissance foot taken from a painting, the paint is very blended, and you can see that you can't see the individual brush strokes. And that is because oil dries quite slowly and it allows you to blend the paint. And on the right-hand side, you can see a similar foot from a Renaissance painting, painted using egg tempera in very small adjacent strokes, which you can actually visually see here. And that's because the paint dries really quickly. That's the first example, and I'll show you a couple more. Once again, the incredible fluid drapery that you can see here in a Netherlandish painting, and on the right-hand side, a contemporary Italian painting where egg tempera has been used, and you can see the individual brush strokes. Still a beautiful painting, but different in technique. And the next image is this incredible, wonderful drapery, the drying oil, again, drying oil here used, and egg tempera here. And this one I included because it has other features. It's got residual old varnish, which has become very yellow in the interstices and cracks. That's something you often see on paintings. There's speckles of old residual materials which have been partially removed, and also some mordant gilding, which has been applied. So real gold sprinkled over a wet oil underlayer or pattern, and it's caught the gold, and that's a technique that's used in Italian painting, usually over egg tempera underlayers. And this is a really staggering example, again, of details from the faces of a Netherlandish painting, an Italian painting. You can see the flesh painting with small strokes in tempera and the incredible blended oil paint. That's just a miraculous piece of painting from a Netherlandish altarpiece in the Prado. I hope you love it. I love it. I love looking at these details. And of course, you can see other things too, like the craquelure pattern, or the cracking patterns are very different on paintings that are made using different materials. So you can begin to identify the kinds of materials that are used and the kind of techniques that are typical for different geographical regions or different periods in painting. And of course, in the 20th century, around about 1962, acrylic paint was introduced by manufacturers. It was slightly earlier in America, and acrylics, again, dry very quickly and allow very even colour field paintings to be produced. And so I've just taken some pictures of acrylics used in painting, and for strange reasons, both images include these very exhausted looking young people. I'm sure that doesn't reflect on the quality of the painting, but it was pretty remarkable that it's not really the acrylic that puts people to sleep, it's possibly the environment in the gallery. Okay, so what about some analytical techniques that are used? I suppose the most traditional analytical technique that's been used, or imaging technique that's been used, is X-radiography. Indeed, X-rays were invented in 1895, and extremely quickly in Germany they were applied to examine painting. So the first X-ray of a painting was made in 1896, only a year after the discovery of X-radiography. And that's really been the bedrock of a technique. We can use X-rays that penetrate really all the way through a painting, provide information of different sorts. And at the top here, I've shown you with the theme of historical application, is a 1970s image of X-radiography as it was done at the National Gallery. We have done this as well in this way, where you have an X-ray tube underneath the painting, there's a hole in the tabletop, and you put an X-ray plate on the top and you fire the X-ray, and then you have to mosaic the sheets together. You move the painting over the surface of the tabletop, and then you can mosaic the images together, photograph them, and fuse them using Photoshop or something. Well, nowadays we have a digital X-ray system. Of course, we don't have to develop hard, acetate films, which was a really stinky process, and for a very long time I used to do it all the time. I very much smelt of chemicals, and those materials really degrade, the acetate and films degrade in a horrible way, giving off acetic acid. So now we have the digital burden of having to, we capture things digitally, and we can fuse the images digitally using very similar setup. But then we have to retrieve the information and make sure it's stored properly. So all of these things come with developmental issues, which I'm sure you're familiar with. What do X-rays show? Just showing just a few examples. They, of course, tell you about the whole thickness of the painting. So you see things like the stretcher bar behind the painting in the middle of the painting. So the stretcher, the wooden stretcher that something's on, also shows all the nails that are used to hammer in the canvas to the stretcher that it's supported on, the canvas painting. So this is Death of Actium by Titian. And what you can see in the X-ray here is that Titian developed the composition not from the underdrawing, but during the painting stage. They've made many changes, and you see many changes here to the position of the bow, and also to the hounds that are leaping up here. There are many versions of the hounds, many changes in composition made using lead white paint or lead white included paint, which is why you see them. You see the arm positions have also been changed. So it's a great example of Venetian painting in the 16th century, and the typical technique, which is to work out the composition whilst painting rather than copying from a drawing and then painting. This is very useful X-rays for looking at that. This is a painting that might be by Gogh, which is in the National Gallery, and you can see that underneath the female portrait is a male portrait. So what you very often see is that there's a reuse of the painting support, in this case canvas. So artists might do this because the commission perhaps wasn't popular, or the person who sat for the painting didn't want to pay for it, or sometimes because the artist was very poor and couldn't afford another canvas. So they simply paint over the underlying image, and in the X-ray you can see this quite clearly. I had to include this one because it's an example of a very obvious forgery, and you don't come across real forgeries that often. It's a painting, a Tudor portrait, and when we X-rayed it, it came in 4 plates, which we had to join together. And underneath there was a writing, and the writing says, "Old masters, for your Xmas gift." So we know that the person who painted this picture must have known that the X-ray would give it away. It's a really great example of a painting on canvas of a Tudor woman, very convincing, but definitely a forgery made since X-radiography was invented. So another technique that's used is in the electromagnetic spectrum, which we use very well for different sorts of analysis and imaging, is infrared reflectography or infrared imaging. And again, I wanted to show you an example from the Courtauld Gallery. Again, a Tudor period painting, which is quite boring, and we don't know much about it. A very brown background. We don't know who the man is. I've tried very hard to identify him from his ring and from his from the inscription, but no real information. But when we looked in infrared, using an infrared sensitive camera, a near infrared image, we could see an incredibly detailed carbon black containing drawing, which has absolutely nothing to do with the top composition, and I've got some details to show you. You can see here an amazing carbon black in a fluid medium. So the infrared radiation penetrates the paint film, most of the paint film, except where there's carbon black used in the paint. So most other paints are penetratable, certainly reds and some blues. and white paint. And so we can see where those paints are used, we can see what's underneath. And you can see this incredibly fluid underdrawing, which was done obviously by somebody completely different. And the portrait was then, the panel for the portrait, the wooden panel, was reused for that top portrait. And because this drawing is so detailed, it's possible to compare the drawing to contemporary drawings or drawings that were made slightly earlier in Tudor period in Antwerp, in other in Belgium, the former Belgian area, the Low Countries, to see whether we can identify the actual author of the underlying composition and then work out the genesis of the painting. So I'll just show you this one, just how detailed it is. What we think is that this work of art, this underlying work of art, was a sketch that was done by a completely different artist, somebody who was responsible for doing architectural designs, who might have done that as a commission. And when that was either approved or not approved, the son, who was a portrait painter, who followed in the next generation, painted the portrait. So sometimes artists handed over their workshops to their children or others who then followed in their footsteps, who might have painted in a completely different style, but reused quite expensive panels for painting and for their commissions. This is a really great and quite fun example of a painting in the Courtauld Gallery by George Seurat. It's a pointillist painting made with tiny dots of complementary colours, so they fuse in the eye, which has been in the Courtauld Gallery, and it's one of Samuel Courtauld's paintings that he gave to the collection very early in the setting up of the Courtauld in the 30s. So we've known, there's been a little bit of art historical study about this painting, that it was made. This is a picture of Madeleine Knobloch, who was his mistress, but his mistress wasn't known to his family. He kept her a secret, and he was painting a picture. And the story goes that when he was painting this picture, somebody came to the studio and said, "You know something, you shouldn't paint yourself in the window looking at your mistress, because it'll be a real giveaway, you know, that everyone will know that you've painted the picture." Now there's been no evidence that this story, which is published and it's been found in the archives, is actually true. But when we made an infrared image, I think you can see that there's a figure in the window right here. I think you see the man, he's got a beard, and his arm is here. So this is the infrared image taken at 1900 nanometers using a special camera. And what I think this is quite convincing, is that this is a detail of the infrared image, and you can see the man with the beard is George Seurat himself. Indeed, he did paint. So we know that the story is true. He did paint himself in the window, and then having heard the comments from his friend about the giveaway, he painted over, let me go back, with a bunch of flowers, which is what we see in the painting today, or a pot of flowers. So in this window, instead of his image, the sort of slightly voyeuristic image, is this pot, which means that it was still hidden and still kept secret. In fact, Madeleine bore him 2 sons, interestingly, so she was quite a serious mistress, but still not known by his family or even acknowledged. Those were the days. I thought I'd add this one in. It's electron microscopy. So when my PhD at the Courtauld, I was captivated by the technique of electron microscopy and how it could show you in great detail information about the surface of paintings and different sorts of deteriorations which occur in paintings. And in the 80s, when I did my PhD, not many people were using the electron microscope for anything really, which just shows how things change. Of course, now it's the fundamental technique for everything that we do. And so I found this very early image of Westby Percival Prescott, who in the 70s used electron microscopy to look at pollen that was in dirt on the picture surface. Now, surface dirt's a big problem for paintings. And I also found these images of UCL equipment that I trained on when I was a student. I think you had to almost pump it down by hand. It was that clunky. And then slightly more modern equipment that we've been using at King's College, Bill Luckhurst, and then even more wonderful equipment, electron microscopes and other sorts of microscopes at the Natural History Museum, and at the Getty, where I got the chance to use an environmental electron microscope to look at the surface of paintings that have water sensitivity that we have to treat. So it's a special project. So in my lifetime, this kind of microscopy has really come on leaps and bounds, and my PhD is very much out of date, but it was nice to have been part of that kind of seminal development of microscopy for paintings. I just wanted to show a few old and new images of the kinds of things we see on paintings. We have lots of deteriorations which are on a micro scale, where we really want to identify what's causing that before we try to treat it, so we can address that quite specifically related to the cause, a bit like the diagnostics in medicine, I suppose. And what I wanted to show you is this is 9 microns, so very small. These are free fatty acids that come from the hydrolysis of oil binding media, and free fatty acids look like this on the surface of a painting, and they can look very white and light scattering on the surface of painting. They can be quite reactive. They can react with metal ions to form complexes, which I'll talk about in a minute. You can also have salt deteriorations. You get crystalline materials that form on the surface of pictures, which might be the result of, again, organic or inorganic chemical reactions with environmental conditions. You can get, on the bottom left-hand side here, you see the effect of cracking of a glare varnish. So it's a fast-drying glare, being the white of an egg, which was very often used as a varnish on old paintings, and it cracks in this way. And then on the lower right corner, you can see lots of mold. You can see free fatty acids, again, these feathery things on the surface of particulate paint film. You can see the binding medium, which looks really soft, and the kind of harder edged pigment particles. And on the top, it's a fungal hyphae, which is also quite common when things get wet on paintings. So we can begin to identify in more detail, once we use electron microscopy, the kinds of deteriorations that we see in paintings, and then use that information. Okay, so it's not only micro changes that happen that we are concerned about, but also macro changes. And I'm going to talk a bit about color change in paintings, which of course affects the way we view pictures now and how we think about them, but we can't necessarily replicate them in conservation. So this is a painting by Bernardo Daddi, Crucifixion from the 14th century, from the Courtauld Gallery. It's one of the panels in the polyptych, multiple polyptych of Courtauld. And what you can see is that it's a detail from the left-hand side of the panel. You can see this wavy line on the left-hand edge, which is where a 19th century frame protected the surface of the drapery of this figure on the left. And you can see that there's a big difference in color between the red protected area that's been protected from light, where the frame was covering up, and the white, or relatively pinky white, of the drapery. And that's an indication that the organic pigment, which is a red lake pigment, has faded. And that has faded quite significantly since the 19th century, presumably because electric lighting was introduced at that time, and the painting received a lot more light than it would have done in a dark church or in storage or in gaslight display, wherever it was. So really, some major changes that have happened in works of art could have happened relatively recently in our time, but not early in their own lifetime. So that's a useful thing to know and to acknowledge, but difficult to treat. So the same painting has another sort of deterioration, which is the darkening of vermilion pigment. So it's mercury sulfide pigment, which goes first grey and then quite black. And you can see it in this painting, the greyish area on the folds of the drapery on the Magdalene's robe, the red drapery. And on the right-hand side, you can see a detail from a painting that's in oil. So the left-hand painting's in egg tempera, but it also happens in oil paint because it happens to the vermilion pigment. And on the lower corner, you can see a detail of replication of blackening of vermilion experimentally by increasing amounts of light exposure. So the very dark grey in the bottom left corner is the most light exposure, and the bright red is where it's been protected from light. And then a little less light has caused it to go a little more grey. So this happens in paintings. We know it's a light-induced change. And there's quite a lot of research on changes in different pigments. And in this case, two researchers in the National Gallery Scientific Department, which is where I was before I came to the Courtauld, have published papers on the blackening of vermilion. Also Dutch researchers have addressed this question. And what it is that you have mercury sulfide, which is affected by sodium chloride, which is present in dirt, but also by light and exacerbated by humidity. And you get various intermediate reactions. So the red changes to corduroy, which is a kind of mercury chloride. And then a grey product of mercury chloride called calomel is formed. So that gives it a shiny greyish texture, which I think you see on the details. And then in combination with sulfur, you get black cubic metacinnabar, or amorphous black mercury sulfide, which is the black material you see. So whilst the reaction pathways have been characterized to some extent, we're still not clear as to why it is that there's such patchy blackening on paintings. And I'm still puzzled by this. I just was a bit at the Louvre last week, and I noticed that in the very hot and humid atmosphere of the Louvre, there were quite a lot of paintings that had suffered from very patchy degradation of vermilion paint. And still, I think the jury's still out on why this patchy happening occurs. So it's not just old paints that change. Some modern paints also change, but not all of them. And one of the main examples of change are synthetic organic pigments. Not all of them, but some of them have faded very quickly. So these are the same painting by Mark Rothko. In 1964, at the top, when he first painted it, which is a sort of deep maroon color, and then by the 1970s and 80s, the painting had changed significantly. So all the red, which had been added to ultramarine paint to make this purple paint, had literally faded, leaving only the blue ultramarine paint. So what we're looking at is a radical change in the overall color of the painting. And the change was in lithol red. So lithol red can be made in different colors, and it was supplied as house paint. So it was used by an artist who didn't realize that that light would change and fade the pigment, and that his overarching, not just this painting, but a whole set of pictures that he made for a restaurant in New York had all changed radically. And we know that he cared a lot about the change in his works and probably would have destroyed them, but by the time they changed, he died, and they were now owned by different institutions who obviously want to show them, even though they've changed. Indeed, we know that all paintings have changed, and if the artists were alive, they might want to destroy them, but because they are handed down to us and because they've probably been bought for a lot of money, people want to display them in any case. So we're looking not at how things were made, but how things have changed, and we need to appreciate that when we're looking at the artist, that it's not the artist's intention we're looking at. So more recently, there's been quite a lot of research into other sorts of changes in paint films, and one of them is this quite interesting technique. I don't know if any of you have ever looked at Dutch paintings, and sometimes you see these very textured lemons, and they look really like lemon peel. So we assume that artists knew something about how lead white, for example, reacted with oil to form metal soaps, which form these kind of very textured paints, would dry in this way, but a bit like lemon peel. So whilst Dutch artists might have known about this, it's not been known by everyone. And what you do get is a kind of deterioration, which is the result of metal soap formation, in this case lead soaps, which can take different forms. So you have the formation of lead carboxylates, which can form this kind of translucent material, and then recrystallization of lead carbonate, which is lead white. And they form these kind of pustules, the lead carboxylates, which can burst out of the surface. And you can see on the top right, some areas where the translucent material has formed a kind of dip or hole in the surface and has popped out. And then in other images here, you can see they've recrystallized into sort of blobs on the surface. Now that on a micro level, it just looks like little white spots, but on a macro level, it can look quite significant. You can get these pock marks that look all over the paint surface, which are a result of metal soap formation. And sometimes they've got little, on the bottom right, little dots of oil on the top, which might be the result of a chemical reaction between oil-containing varnishes and the lead in the paint film, lead or zinc in the paint film that typically form soaps. So not all artists knew about these changes, and we still don't know how quickly they form and why. So we have no idea that they form. But we know that in the lab they form very quickly, but we don't know the time scale of formation in artists' paint. So we don't know whether the artist intended for this texture to be formed, or whether they're just deteriorations which the artist wouldn't have liked. Linked with the same chemical reaction, so soap formation, the form of translucent metal carboxylates, is the increase in transparency of paint films. And very often you see this on the painting. Here's an example from Jan van Scorrel's 16th century painting, where the pink flesh paint and the lead in the pink flesh paint has reacted to form carboxylates, which are more transparent than the lead carbonate, which is the white pigment. And so the paints become very transparent, and you can see the black underdrawing lines. You can see the lines of the hair and the shadow for the neck. So that's become more pronounced. Even the veins in her forehead, which have been underdrawn in carbon black, that's become more transparent with time. Again, we don't know about the time frame, so we don't know whether this happened rapidly after the paint dried. We think not, or after some time frame. That's the subject of quite a lot of research, current research. Here's another example from Sebastiano del Piombo, which is Kingston Lacey in a National Trust property in Dorset, where you can see the man who's, this is the judgment of Solomon, so divided. You can't see, there are many changes in this composition, you can't see them all, but the story obviously goes that the two women are claiming that the baby is theirs, but Solomon decides to say, we're going to chop the baby in half, and of course the real mother says, don't do that. And it's a terrible story. But what you can see here is the man who's just about to chop the baby, which hasn't been painted in the composition, but what you can see is another figure underneath that. Through the paint has become more transparent with time. So you can see that reworking, there's an arm extended and the head here. I hope you can see that. So the paint, increased transparency of the paint really makes a significant difference, and sometimes reveals earlier compositional elements which have been covered up. Okay, so amongst the other chemical changes that happen are, and I put some in where we don't know the cause, subject of research or current research, the darkening of copper green pigments in paint. So you could have copper acetate or copper chloride, which is usually formed by taking copper metal and putting it in some kind of acid, scraping off the kind of bluish, greenish pigment, and then mixing it with oil. And you see this in a paint cross-section on the right-hand side, a sample taken from this painting by Polai Olio in the National Gallery, where the paint film's actually gone completely brown. It's completely gone brown. Copper greens don't always change to brown. Sometimes you get iridescently bright copper greens that are just the same age, but sometimes they completely brown. And what you see in a cross-section, this is actually a thin cross-section, so it's a thin section. Light shining from underneath, is that the actual binding medium, the oil, is actually yellowed, but there are also these dark particles, which recent research, and again, the meeting I was at Paris last week suggested that copper oxides are formed, which are brown, which cause the paint film to darken. And this is based on experimental evidence, not samples from paintings, by the way. So often there's a quite interesting gap between the kind of chemical type research that's done on model systems and the real situation, which is more complex in paintings. And I kind of sit in the middle there, trying to learn from the molecular level studies, but also bring that to real situations in paintings for conservation. Another staggering change is the organic pigments that are used to color paint. One is yellow lake pigments, which could be based on materials like weld and broom, so natural materials, that fade really, really quickly in light. And there's some great examples of this where you have blue leaves, which were originally, of course, a mixture of blue and yellow to make green. These details are from Dutch paintings. The top one is from a painting by Pijneke, in a 17th century painting by Pijneke, which is in the Dutch Picture Gallery, and the other are sort of blue foliage from other paintings from the same period, where yellow lake was used and has faded. We have fantastic pictures by two fantastic paintings by Vincent van Gogh. We had a recent exhibition of Van Gogh's self-portraits, our own one, and quite a few borrowed paintings. And we've done quite a lot of technical research together with Dutch colleagues and people at the Metropolitan Museum of Art. And also what's really interesting about looking at changes in Van Gogh's paintings is that he had his letters, which were written largely when he was not living in Paris. He wrote to his brother about paintings and how he felt about materials, and his brother, who was an art dealer, and Vincent van Gogh was very poor, supplied all his materials, bought them for him, but Vincent asked his brother for various different colours, some of which he knew would change. So that makes it very interesting to look at documentary sources and to look at paintings and to also do experiments on the materials that we know the recipes for. So there's a few quotes from his letters. So some of the paintings are only to be found in Delacroix, who had a passion for the two colours that are most condemned, and with most reason, citron yellow and Prussian blue. So he was aware of his materials, the yellow pigment, citron yellow, which is cadmium yellow, he knew what browned, and Prussian blue, which was a blue pigment, which was invented in about 1700 and was used very quickly after that, which also went green sometimes. So one of the main causes of change in Van Gogh's paintings, but also in Impressionist paintings that are made using the same materials, because by that time, artists were buying things from Cullinan. They weren't making things in their own studio. So they were using similar materials, which had similar chemical changes. And so there have been a lot of research where we've made from 19th century recipes, both the pigments themselves and the organic pigments, but also made the paints and tried to replicate those changes by artificial aging. So we're exposing to light and different humidity and temperature to see whether we can accelerate the aging of these materials and look at their relative stability. And on that basis to provide information about how we view our paintings now, how they've changed. So here we are making different sorts of lake pigments using these recipes from the raw materials, which might include madder, and there were 1 or 2 synthetic lake pigments. There was synthetic purpurine lake. They might be made from kermes, beetles, or lac insects, the exudates from lac insects, which came from different places like South America, the new colonies. So there were different sources. Mostly there were natural lakes at the end of the 19th century, but it was the beginning, 1868 was the beginning of synthetic lake production. So we included that in some of our experiments. And then tried to relate those changes back to what we see in the paintings. So this is the landscape orchard, which is a Courtauld picture, and an example of purpurine, synthetic purpurine containing lake, which I hope you can see the detail of here, that's used for the branches and the trees. And then there are some experimental samples. You can see it in ultraviolet light and in normal light, and then faded and unfaded. And what you see is this is a relatively stable material. So not all these synthetic or natural lakes fade. Some of them fade more than others. And it's very useful for us to know which ones fade the most, so that we can estimate in a kind of empirical way how much things have changed, the relative rates of fading. So one of the things that come in the letters, and there are some paintings that really have changed a lot, and there are some examples here, where the area that's protected from light on the left-hand side of this middle image, you can see is much pinker, and where it's exposed to light, it's become either yellowy or completely discolored. And some of these paintings have literally changed very radically. But we know from a letter from 1888 that he wrote to his brother, he said, all the colours that Impressionists have brought into fashion are unstable. So that's all the more reason not to be afraid to lay them on too crudely. Time will tone them down only too much, which means he understood that you had to apply them more thickly if they were going to retain their colour. So we get a sense of the artist's care for the longevity of his works. So this is, its geranium lake was one of the earliest lake pigments that was synthetic, which was applied. It was called geranium lake, and it contained a bromine identifying element, and it's called eosine. So that's something we know faded within about 5 years completely. So we know that all the eosine lakes that are used in the late part of Van Gogh's paintings have completely disappeared, and this has had a radical effect on the appearance of the paintings. Another thing about Van Gogh's paintings, which is interesting, is that there are obviously lots of forgeries of paintings, and people want to claim that Van Gogh, they've got a Van Gogh, you know, but actually there's a fantastic way of linking the paintings together using this weave pattern method, which looks at the relationship between commercially primed canvases, that's canvases that were cut from a big roll of canvas, which is commercially prepared, and how the weave patterns relate to each other. So we know that Theo, the brother of Van Gogh, supplied not only colours, but also pre-primed canvas for use on a big roll. And so we can piece together, based on the weave pattern of the digitally examined weave pattern of the canvases, based on the X-radiograph, we can see the relationship in the thread counts of the warp and weft for different rolls of canvas. So we can piece together the bit that he cut off for a particular painting and how that related to the roll that he used. So we can identify all the paintings on canvas and almost their dates by this weave method, this based on X-radiography, the weave pattern, which is unique for each piece of cloth. Dating panel paintings, or at least oak paintings, can be done by dendrochronology, which looks at counting the growth rings in the panels that are cut from oak trees. So here in this image, you can see Ian Tyers. There's a couple of experts in the world who do this, and they literally look under the microscope at the end grain and then count the tree rings. And based on that, you can date the actual piece of wood, or at least the felling date of the piece of wood. And on that basis, you can date the likely, or look at the likely date of the use of the panel by the artist. So the felling date would be followed by a period of seasoning and resting of the wood. So 5 or 10 years later, the wood would then be used. And this is a painting, Cain Slaying Abel by Rubens. So it's a way of dating the actual wooden panel, which is quite useful and quite reliable, based on databases of mainly oak panels. So finally, and I have been talking for rather a long time, so you might be exhausted by now, I just want to mention the way that paintings, one of the things about painting conservation, which is a little bit controversial, and that is the removal of natural resins or resin varnishes which have changed colour. And I wanted to show you a couple of details of cleaning, during cleaning. So you can see the yellow varnish, and then the areas that look lighter is where the varnish has been removed. And one of the areas of research that I've been involved with is looking at chemical changes in paint as a result of cleaning. So there are lots of different methods of cleaning. And what we do is we seek to remove this varnish or remove material from the surface of pictures so that we can see the painting again and display it with the new varnish more saturating. The yellow flattens the image, and when you remove it, you can see a great deal more detail, and the colours are much more lively and vibrant. But the process of removing varnishes entails some risks, because we use organic solvents, but we can also use gels and reagents of different types. So my own research is looking at the risk evaluation of different methods for cleaning. But I wanted to show you just some details of how different paintings look when you remove the varnish, which also disguises, you can see on the left-hand side, all kinds of damages and abrasion to the paint film. So that harmonizing yellow varnish can also disguise other old retouchings or damages that you see in paintings. So they aren't, when you see paintings in galleries, they're all damaged and they've all been restored so that you can't see the damages in those cases. And this is my final image. I wanted to show you, this is a new development. It's the use of hyperspectral imaging to infrared, in the infrared, to look at this painting by Gogh, which is in the Courtauld Gallery, Nevermore, which is a very famous nude, and a series of images taken using increasing wavelengths in the infrared range, which showed us something about the underlying composition which we didn't know before. This is a new development in technical imaging and analysis. And the final slide shows, and I hope you can see this, that underneath this figure is a farm scene, and there's a picture of a mule. I don't know if you see right in the middle, there's a mule that's painted underneath the belly of the woman. And there's no other analytical technique so far that has been able to reveal this. So the application of infrared in this case, with increasing wavelengths, has told us something about a picture, something beneath the surface that we couldn't see with any other technique. And I know, to conclude, that this is going to be the way of the future. There'll be new analytical techniques, mostly non-invasive methods where you don't take samples, where you discover new things about works of art that haven't been discovered before, even very old works. So thank you for listening. And if you have questions, I'll be very happy to try to answer them. I'll stop sharing my screen.
Thank you very much, Aviva. That was a great talk. Full of fascinating detail that we would expect from you. So thank you very much for that. I have a number of questions, and I'll start off with a question of my own. How do you decide which painting to work on? Do they come up as a result of request that you look at such and such a painting, or do you sometimes make that decision yourself?
Usually for the Courtauld Gallery, we have curators who for various reasons may want paintings to be conserved. It could be that they're going to be loaned to an exhibition, or the focus of an exhibition, or that they have exhibited various sorts of deterioration, which are like very dark yellow varnish, or splits in wood that need to be repaired, or delamination of paint. So there may be structural reasons or aesthetic reasons why curators may wish to do that, and we'll provide advice about that. Or we also have take on pictures from regional museums where they don't have their own conservation departments, and we choose pictures that are of high quality so that they're interesting for us to both technically study and to conserve. Sometimes we take things from private collections too, or private organisations.
That brings up two questions. The questions are beginning to pile in now. That raises two questions. Firstly, do you do a lot of international collaboration with other art galleries and conservation departments abroad, for example?
Yes, we do. Most of our research is done in collaboration with others who are expert in various analytical techniques that we don't have. So, for example, the University of Amsterdam, or there's a research institute called the RCE in Amsterdam, I've worked with for about 20 years. We've collaborated with other organisations in the UK, in Italy, University of Pisa, the chemistry department most recently. We work with Tate, sometimes with the National Gallery. Yeah, I mean, there are many collaborations that we make which involve either analytical resources or other sorts of expertise.
And I've just been asked, how many places in the UK have the capability of doing the kind of technical examination of painting?
Most of the major museums do have resources. So the National Gallery, Tate, and there are some private organisations that have these sorts of resources where you can pay to have that done. Indeed, we offer a service for private clients who want technical analysis done, for which we charge. So the major museums, I would say, have the resources to do this sort of work.
Okay, thank you very much. We have a couple of related questions. I mean, it's interesting how even modern artists have problems with pigment deteriorating and so forth. So this raises two questions, one of which come from me and the other one come from a member of the audience. Firstly, to what extent were early painters aware that there could be future problems with their painting? I mean, did it strike them that in 100 years' time or 400 years' time, we might have a problem seeing their painting properly?
Do you mean early painters?
So were painters like Leonardo da Vinci, for example, aware that there could be problems with their pigment?
A lot relies on documentation, and I gave the example of Van Gogh, who did apparently have that he's 19th century, and of course he's dead, and his letters record information about how he was concerned about his materials. But that's fairly rare, because most artists don't write about their techniques. There are a few. You're talking about historical artists, but nowadays the Tate, for example, have a database of artist interviews where they ask questions about whether artists care about their materials, and some of those artists have died, but they have a stock of recorded information. So if the artists themselves don't write about what they do and what they care about, which is most cases because they're too busy making the works of art, apart from Van Gogh, who did write about it, so I did use that example. Leonardo, I can't say, because I don't think he wrote about his materials in such a way, didn't write about the preservation of his works. You know, he did a great deal of writing, but not about that. So I can't say that for every artist. There are a few artists who've written historically about it, like Van Gogh, but mostly the information is drawn on artist interviews for contemporary art and contemporary artists, 20th century artists.
Now, to take the modern situation, are paint technologists working on paints that will resist the effects of time and light?
Well, we've had quite a lot of discussions with, for example, Winsor & Newton, who are producers of artist paints. Their research and development department certainly do tests for every batch of paint that's made, mainly for touch drying. So what they aim to do is to make sure that the range of paints that are being supplied dry in equivalent amounts of time, and they can adjust the formulations of those paints accordingly to make them dry a bit faster or less fast. Now, manufacturers won't tell us exactly what's in paints, because otherwise that's their trade secret, but they're certainly aware of colour fastness, and very often on the tubes of paints you get a colour fastness code. So all kinds of pigments are supplied, but some of them are more colour fast than others. So whether they remain the right colour that they were intended relies on a number of different things. So it might remain, or it might also be influenced how the paint's used, how much light's exposed to, whether it's exposed to environmental fluctuations in humidity. All of these things might influence change. So there are combinations of technical factors, but also manufacturing, which will will influence it. I'm not sure that answers your question though. Do we work with manufacturers? No, not really, but we certainly talk to them.
Yes, okay. We've got quite a significant number of questions here, so I'm going to do them in more or less time order now. Is it difficult to restore light-affected watercolors?
I'm not a watercolor expert, and that is a good question for a paper conservator. Although if the colors and the paint's affected by light, you can't restore it. You can only do what you can with what's left. So you wouldn't repaint it. You could project onto the surface what you thought might have been there. That's what people have sometimes done, but you can't bring it back. No, I don't know if that answers the question that the person asked.
Now, I've had a question here from Christine Hostock, who is a pigment specialist, and she says, in the cross section you showed near the beginning, how did you identify the pigment in it?
Okay, so there are lots of different ways of identifying materials in cross sections. You can use microscopy. So if you're an experienced microscopist, and I would say I am, then you can identify them based on color, but there's only so far as you can do that, because you can use elemental analysis, so SEMEDX, where you can map the elements in materials, and you can also do point and shoot, and you can work out what elements are present. With organic materials, you can use FTIR and Raman spectroscopy. On cross sections, you can map them, and that provides chemical information about the bonds in materials. So you can work out what some inorganic materials are, and sometimes the class of organic materials based on those three techniques.
So do you use X-ray fluorescence spectroscopy a lot then to identify elements?
Yeah, we do. We have two methods of XRF. One is static, so it's like a handheld device, which has about a 6 millimeter resolution, not great resolution. And when you have paint layers, of course, the X-rays go all the way through, so you get the information from all the layers, which is complex and to pick apart unless you have a cross section where you can identify the individual layers. So the combination of samples and XRF. We also have XRF mapping, so we have a scanning system which allows us to look at a macro image. Again, the interpretation might require a cross section, I think, because we have to understand what layers are there. So we get elemental information. The light elements aren't really easily picked up, so anything lighter than aluminium is not really detected with macro XRF or handheld XRF. But good non-invasive methods.
Good.
Yep.
Now here's a completely different sort of question. How precise can you be in ascertaining the binder type in oil painting?
Good question. So we don't have resources for that. That's one where we do collaboration. So mass spectrometry. So either gas or liquid chromatography is the best way of identifying different sorts of organic materials in painting. So I think for dyes, liquid chromatography is the key technique with mass spectrometry. So you can look at the actual molecules, break them apart and look at their characteristic fragments. And for different types of oil, so with FTIR and Raman, you can't tell what kind of oil it is. You might see some lipidic absorption bands, or you might see some absorption bands for protein, but you won't know what kind of protein or oil is there. So you need something which tells you what the mass fragments are. So some kind of mass separation technique with mass spectrometry is needed.
Okay, you use mass spectrometry as well. So you're using a really wide range of techniques, in fact.
Well, it is used, but I personally don't. I work with people who do. What I find boggling is that I can't be an expert in everything. We do use this toolkit where we have Raman and FTIR microscopy, we have SEMEDX, we have macro scanning, but all of that, the data processing, it's a lot to be an expert in, as well as deciding how pictures are restored and actually doing it. So I find that we have to rely on experts, so GCMS, for example, or liquid chromatography. The kit breaks down the whole time. The columns get ruined all the time. So we need experts to do those are really expert techniques. I think very much. Yeah. So
very much a team effort as well.
Yeah, it's a team effort, like most science, I guess, is a team effort.
Now here's a question. Do you find it difficult to look at painting without using your technical eye, just in the same way that hi-fi enthusiasts tend to focus on the speakers rather than the music?
I have no problem looking at paintings without any technique. I love looking at paintings. That's what's behind why I do the job. I am absolutely perfectly capable of not looking at deterioration or to look at the image. I'm really interested in the history of art, and that's a whole other lecture, but you've asked me to talk about science, so I'm doing it. But, you know, I love looking at paintings for all kinds of other reasons than deterioration or damage or whatever. But yeah, my job is to do the science of it. So yeah, but I love looking at paintings. It's my main passion. Yeah. Also making art, although I'm not good at it, obviously, compared with the great paintings that I get to look at.
Good to hear. Good to hear. Now I've got one final question, and one new message come up. Just make sure that it's not. Yeah. Lots of thank you, by the way. Lots of people saying a wonderful talk. But could I perhaps end with one question, and that is, have you ever had a painting which has completely confounded you, where the result have sort of, you think, what on earth is this, you know, where
Yes.
you...
Lots of paintings.
Right,
Well, there's lots of things I come across all the time. It's very stimulating, because there are times when a student will say, you know, what's this overall accretion or something, and I really don't know, and I'll say, well, let's investigate it. Lots of things come up where, and also decision making where you're not sure what to do. Yes, of course, and it's very challenging, and that's where the difference between model systems and science, where you have controlled variables and draw conclusions based on these very narrow range of variables, conflicts with the kind of things we deal with, which are very complex and have long physical histories and different sorts of materials combined. And so that conundrum presents itself all the time, I would say.
Well, I think that's a very good point on which to end. So we're sort of able to get on exploring your paintings, and thank you again for a talk which was not only fascinating in itself, but contains such an enormous amount of interesting detail, from the conversion of mercury sulfide to another form of mercury sulfide to the complete failure of modern paint as well. So thank you very much again for giving such a wonderful talk with, I would like to say, lots of chemistry in it. So that's very good.
Thank you.
I just say to the audience, thank you very much for coming. 58 people this week, so we're keeping up the numbers despite all the competing attractions post-lockdown, so we hope to keep this going. Next month, Alan Dronfield, who gave the very first talk in July 2020, you remember that, right in the middle of the first lockdown, he will be talking about the discovery of chirality. So that's awaiting us next month in July. So please join us again in July for yet another fascinating talk. And for now, goodbye, and thank you, Aviva, once again for such a lovely talk.
My pleasure.
Bye.
Bye.
Bye.